There is a military Jeep sitting in a Pennsylvania barn. It has been there since 1946, exposed to rain, exposed to humidity, exposed to 80 years of complete neglect. And yet, when collectors finally pulled it out, they found something that should not exist. The original olive drab paint was still there. Faded, yes. Worn in places. But not peeling, not flaking, not failing. Now look at your fence, the one you painted 3 years ago. The paint is already cracking, already peeling, already failing. Modern paints promise advanced chemistry. They promise better coverage. They promise environmental safety. But they fail within years, sometimes within months. The difference is not technology. The difference is ingredients. World War II paint contained chemicals that modern regulations have banned or restricted. Zinc chromate, red lead, white lead, linseed oil with metal dryers. These were not random choices. Each ingredient served a specific purpose. Each chemical performed a specific function. Together, they created coatings that lasted not years, but decades. Today, we are going to break down every single ingredient that went into World War II-era paint. The exact formulas, the exact percentages, the exact chemistry that made them work. This is not nostalgia. This is science. And by the end, you will understand exactly why an 80-year-old Jeep has better paint than your 3-year-old fence. Let us begin with the most important ingredient of all. Number 1. White lead. For over 2,000 years, one pigment dominated the paint industry. White lead. Chemical name: basic lead carbonate. Chemical formula: 2 parts lead carbonate combined with 1 part lead hydroxide. Written as 2PbCO3.Pb(OH)2. This single compound contained approximately 70% lead carbonate and 30% lead hydroxide. In 1949, a typical White House paint label showed this exact formula: basic sulfate white lead at 11.1% of total paint weight. Within the pigment portion alone, that jumped to 18.2%. The traditional white lead paste that painters mixed on site was even more concentrated: 88% lead white pigment, 10% linseed oil, 2% turpentine. That is almost 90% lead by weight. Why did painters use so much lead? Because lead did things no other pigment could do. First, lead white dried faster than any other white pigment. The lead itself acted as a drying agent, accelerating the curing process. Second, lead white had exceptional hiding power. One coat covered better than 2 coats of modern titanium white. Third, lead white created flexible films. Unlike brittle modern paints, lead white paint could expand and contract with wood without cracking. Fourth, lead white was self-leveling. Brush marks disappeared as the paint settled into a smooth, uniform surface. Fifth, lead white resisted moisture. Water beaded on the surface rather than penetrating through to the wood beneath. Number 2. Linseed oil. If white lead was the king, linseed oil was the foundation of the entire kingdom. Linseed oil comes from flax seeds, the same plant that produces linen fabric. Humans have pressed oil from flax for over 6,000 years. What makes linseed oil special is how it dries. Modern latex paints dry through evaporation. The water leaves, and a plastic film remains on the surface. Linseed oil does not evaporate. It undergoes a chemical reaction called oxidative polymerization. When linseed oil contacts oxygen in the air, the oil molecules begin linking together. They form long chains. Those chains create a flexible, durable film that is chemically bonded to itself. This process does not stop after the paint feels dry to the touch. It continues for weeks, sometimes months. The paint literally gets stronger over time. The traditional recipe was simple but precise. For a full coat, painters mixed 1 part dry pigment with 2 parts boiled linseed oil, adding a small amount of turpentine to improve flow. For thicker applications, they reversed the ratio: 2 parts pigment to 1 part oil. The exact percentages in a finished paint were typically dry pigment at 60 to 75% by weight, boiled linseed oil at 25 to 35%, turpentine at 2 to 5%, metal dryers at 0.5 to 2%. There were 3 types of linseed oil available. Raw linseed oil dried slowly, taking 2 to 10 weeks to fully cure. Boiled linseed oil contained metal dryers that reduced drying time to 1 to 2 days. Stand oil was heat-treated for even greater durability. The critical difference between linseed oil and modern binders is penetration. Linseed oil soaks into wood fibers. It becomes part of the wood itself. Modern latex sits on top of the surface like a plastic sheet. When moisture gets under that plastic sheet, it has nowhere to go. The wood rots. The paint peels. Linseed oil paint breathes. Moisture can move through it. The wood stays healthy. The paint stays attached. Buildings painted with linseed oil in the 1800s still have original paint in protected areas. That is the power of a living binder. Number 3. Zinc Chromate. When World War II began, the United States military faced a serious problem. Aircraft, tanks, and ships were failing not from enemy fire, but from corrosion. Salt spray, desert sand, tropical humidity. Metal was rusting faster than it could be repaired. The solution came in a distinctive yellow-green color. Zinc Chromate. Chemical formula: ZnC004. Molecular weight: 181.4 grams per mole. The United States Navy designated it Formula 84. It became the standard primer for every aircraft, ship, and military vehicle in the American arsenal. The composition was straightforward. Zinc chromate pigment as the primary corrosion inhibitor. Toluol, also known as toluene, as the thinner. Linseed oil or alkyd resin as the binder. Application specifications were precise. Thickness between 7/10,000ths and 1,000th of an inch. Drying time of 8 hours between coats, 1 to 2 coats required. But the magic of zinc chromate was not in its application. It was in its chemistry. Zinc chromate is slightly soluble in water. When moisture contacts a scratch or damaged area, it dissolves a tiny amount of the primer. That dissolved zinc chromate then reacts with the exposed metal surface. It creates a new protective layer directly on the wound. The primer literally heals itself. Every time it rains, the process repeats. Damage, dissolution, protection, healing. Modern primers do not do this. When they are scratched, the metal underneath begins corroding immediately. Zinc chromate primers contained hexavalent chromium, a known carcinogen. Modern regulations have banned or restricted their use for good reason. But nothing developed since has matched their self-healing capability. 80 years later, aircraft recovered from World War II crash sites still show zinc chromate primer protecting the aluminum underneath. The yellow-green color has faded. The self-healing chemistry has not. Number 4. Red lead. Ships presented the ultimate challenge for paint chemists. Constant immersion in salt water. Endless cycles of wet and dry. Biological growth, trying to attach to every surface. The answer was the oldest anti-corrosion coating known to humanity. Red lead. Chemical name: lead 2,4 oxide, also called minium. Chemical formula: Pb3O4. Color: bright orange-red. The formula was simple but effective. Red lead pigment at 85 to 90%. Linseed oil at 10 to 15%. The United States Navy specified it under MILP 17544 for shipboard applications. Red lead had one property that made it irreplaceable. It formed a chemical bond with steel. Most primers create a mechanical bond. They grip the surface through texture and adhesion. Red lead created a molecular bond. The lead oxide actually reacted with the iron and steel, forming a compound that was part primer, part metal. This bond did not peel. It did not flake. It did not fail. The Golden Gate Bridge depended on red lead primer for most of its history. Ships that served through 2 world wars still had functional red lead coatings when they were finally scrapped decades later. Red lead had another unique property. It dried faster than any other pigment when ground in oil. A painter could apply red lead primer in the morning and top coat by afternoon. With other primers, that would take days. Red lead was banned in 1992 in the United Kingdom. Restrictions vary by country, but residential use is prohibited almost everywhere. The replacement zinc-rich primers work through sacrificial protection. The zinc corrodes instead of the steel, but they do not form molecular bonds. They do not become part of the metal. Red lead did, and that is why ships from the 1940s showed less corrosion than ships from the 1990s. Number 5. Metal dryers. There was one problem with linseed oil paint. It dried slowly, very slowly. Raw linseed oil could take weeks to fully cure. In a construction environment, that was unacceptable. The solution was metal dryers. These were compounds containing specific metals that catalyzed the oxidation process. They made linseed oil dry faster without changing its fundamental chemistry. The most common dryers in World War II era paint were lead dryers, which promoted both surface drying and through drying. Typical concentration was 0.5 to 1% of oil weight. Cobalt dryers, which accelerated surface drying dramatically. Concentration was much lower, only 0.02 to 0.05%. Manganese dryers, which promoted through drying of the entire film. Concentration ranged from 0.02 to 0.1%. Two specific lead compounds were widely used. Litharge, which is lead oxide with the formula PbO. Sugar of lead, which is lead acetate, used in preparing boiled linseed oil. The process of making boiled linseed oil actually did not involve boiling in the traditional sense. Manufacturers heated raw linseed oil with metal compounds. One historical recipe called for 1 part white lead, 1.5 parts litharge, 1.5 parts sugar of lead, 1.5 parts red lead, 12.5 parts linseed oil. This mixture was heated until the metals dissolved into the oil, creating a dryer that would cure in days rather than weeks. Modern paints use cobalt and manganese dryers without lead. They work, but not as well. Lead dryers promoted a specific type of cross-linking in the oil that created harder, more durable films. Without lead, modern oil paints cure softer and remain more vulnerable to damage. Number 6. Olive drab. Every American military vehicle in World War II wore the same color. Olive drab. Not olive green. Not army green. Olive drab. The distinction matters because the exact formula was specified down to individual pigment percentages. United States Army Specification 3-1 established the color in 1920. It remained unchanged throughout the war. Quartermaster color number 22 was the official designation. The pigment recipe was precise. Yellow iron oxide at 18%, medium chrome yellow at 7%, lamp black at 3%. The remaining 72% was binder, typically linseed oil or synthetic alkyd enamel. The finish was specified as lusterless, meaning flat or matte. No gloss, no shine, nothing to reflect light and reveal position to the enemy. In 1940, the Army issued specification ES number 474 for the lusterless enamel formulation. The paint had to meet strict performance standards. It had to adhere to bare metal and previously painted surfaces. It had to resist chipping from vibration and impact. It had to withstand temperature extremes from desert heat to Arctic cold. It had to maintain color stability under intense ultraviolet exposure. Problems emerged during the war. Shortages of cadmium pigment required reformulation. Some manufacturers could not obtain proper color charts and produced paint that did not match specification, but the basic formula never changed. Interestingly, the Army Air Forces used a different olive drab. Dark olive drab 41 was darker than the standard Army color. It was standardized in October 1940 for aircraft applications. There were political battles over unifying the two colors. The Air Forces resisted because their formulation had special properties that prevented detection by infrared film. In the end, both formulations survived the war, and both lasted for decades on the equipment that wore them. Number 7. The four-coat military system. World War II military specifications did not just define paint, they defined systems. A complete military paint system required 4 separate layers, each with a specific function. Layer 1 was the primer, Formula 84, zinc chromate base with toluol thinner and linseed oil binder, applied immediately after surface preparation. Thickness between 7/10,000ths and 1,000th of an inch. Drying time, 8 hours minimum. Layer 2 was the anti-corrosive coat, Formula 14, red lead or additional zinc chromate depending on application, applied over the dried primer. Drying time, 4 hours minimum. Layer 3 was the undercoat, color matched to the final top coat, built additional thickness, provided a uniform base for the finish color. Layer 4 was the top coat, olive drab for vehicles, haze gray for ships, The final protective and camouflage layer. The total system thickness was specified not to exceed 0.02 of an inch, or 2 mils. This seems thin by modern standards. But the specification was deliberate. Thin coats do not crack, thick coats do. Each layer was thin enough to remain flexible, but thick enough to provide protection. The 4-layer system created redundancy. If one layer failed, 3 others remained. Surface preparation was equally specified. All rust and mill scale had to be removed completely. Acid pickling or sandblasting down to bare metal. Grease removed with solvents. Surfaces completely dry before painting. No shortcuts, no rushing, no exceptions. Modern painting rarely follows this discipline. Contractors apply thick coats to finish faster. Surface preparation is minimized to reduce labor costs. The military specifications worked because they were enforced. Government inspectors verified compliance at every factory and shipyard. When paint failure meant mission failure, there was no tolerance for shortcuts. Number 8. The supporting ingredients. Beyond the primary components, World War II paints contained dozens of supporting ingredients. Turpentine was the universal thinner. Distilled from pine tree resin, turpentine dissolved linseed oil and improved paint flow. It evaporated slowly, giving painters time to work. Typical concentration was 2 to 5% of the total formula. Zinc oxide served multiple functions. Chemical formula? Zenno. It provided white color with less toxicity than lead. It improved mold resistance. It enhanced the drying action of linseed oil. Many paints combined zinc oxide with white lead to balance performance and safety. Various earth pigments provided color. Yellow ochre, which is hydrated iron oxide with formula Fe2O3.H2O, created yellow-brown tones. Red iron oxide, Fe2O3, provided red-brown colors. Lamp black, pure carbon, delivered deep black. Chrome yellow, lead chromate with formula PbCrO4, produced bright yellows. Chrome green, chromium oxide, Cr2O3, created greens. Prussian blue, iron ferrocyanide, gave deep blue. Lithopone was a cheaper white alternative. A mixture of zinc sulfide and barium sulfate, it provided decent hiding power at lower cost than white lead. By the 1940s, titanium dioxide was entering the market. Formula, TiO2. It offered excellent hiding power without lead toxicity, but early titanium dioxide had problems. It chalked rapidly under sunlight. Manufacturers were still learning how to stabilize it. The transition from lead-based to titanium-based white pigments happened gradually through the 1950s and 60s. By the time lead was banned in 1978, titanium dioxide had become the dominant white pigment, but the formulations were different. The chemistry was different, and the performance was never quite the same. Number 9. Why each ingredient mattered. Let us summarize why each ingredient contributed to the legendary durability of World War II paint. White lead dried fast because the lead acted as a catalyst. It created flexible films that moved with the wood. It hid imperfections in a single coat. It resisted moisture infiltration. Linseed oil penetrated rather than sitting on surfaces. It cured through oxidation, getting stronger over time. It allowed moisture to escape rather than trapping it. It bonded with wood at a molecular level. Zinc chromate healed itself when scratched. Every exposure to moisture renewed the protective layer. It worked on aluminum, steel, and iron. It required no maintenance once applied. Red lead bonded chemically with steel. It created a primer that was part coating, part metal. It dried faster than any other primer. It lasted for decades under the most demanding conditions. Metal dryers ensured complete curing. They created hard, durable films. They allowed linseed oil to dry in days rather than weeks. They promoted cross-linking that improved strength. The four-coat system created redundancy. Each layer served a specific purpose. If one failed, others protected the substrate. Thin coats remained flexible, while thick systems cracked. Proper surface preparation ensured adhesion. Clean metal bonded with primers. Contaminated metal did not. No amount of good paint could overcome poor preparation. Every ingredient worked with every other ingredient. The system was designed as a system. Remove one component, and the whole structure weakened. Modern paints have removed the most effective components for legitimate health and environmental reasons. But nothing has replaced them with equal effectiveness. That is why 80-year-old military equipment survives while 5-year-old residential paint fails. There is a Jeep in Pennsylvania with 80-year-old paint. Now you know why. White lead that dried fast and flexed with the wood. Linseed oil that penetrated and cured over months. Zinc chromate that healed its own scratches. Red lead that bonded chemically with steel. Metal dryers that ensured complete curing. A 4-coat system designed for redundancy. Surface preparation that accepted no shortcuts. Each ingredient served a purpose. Each chemical performed a function. Together, they created coatings that lasted generations. Modern paint has removed most of these ingredients. Lead is banned for good reason. Hexavalent chromium causes cancer. The regulations that restrict these materials protect human health. But protection came with a cost. The average exterior paint job now lasts 5 to 10 years. Homeowners spend thousands of dollars repainting surfaces that their grandparents painted once. The paint industry does not mind. Shorter product life means more frequent purchases. But you do not have to accept this trade-off. Linseed oil paint without lead is still available. Zinc-rich primers still work. Proper surface preparation still matters. The 4-coat system still functions. The technology exists. The knowledge survives. The question is whether you are willing to apply it. That Jeep in Pennsylvania proves what is possible. Your fence can last just as long. If you use the right ingredients,